Assalamualaikum, hello everyone. In this lecture, we are going to learn the basic of acoustic design. In designing for acoustic, there are a few things to take into account. First is the activities to be performed. Is it office, concert hall, auditorium, and etc. Then we have to figure out what is it that we are trying to solve. Is it noise or more to improving acoustic experience? And then if it's noise, where is the source, for example? We also need to consider the sound spectrum, loud or soft, high or low frequency, and we have to consider what are the construction systems and what materials to be used. Now, as an architect, having the basic knowledge is very important. Yes, you can hire an acoustic engineer, but that is if you are building a big concert hall, for example. Okay. Now, remember how in previous lecture we learned that noise affects our daily life and can cause hearing disabilities, stress, and a few other problems. So please remember that whatever we build will affect the user. So later in this lecture, we are going to explore how to improve acoustic comfort in different building types. Before that, let's learn one of the sound effects produced by reflections and see the importance of it. So what is dead room, reverberation, and echo? Let's take this auditorium, for example. So when we talk in front at the stage, sound will reach audience directly. And some of the sound will be reflected at the ceiling or wall and then again reach the audience. If the reflection of sound from here compared to direct one here, okay, if the reflection of sound reach at similar time with the direct sound, then it is acoustically good. But prolonged sound combined with direct sound creates reverberation and echo. Reverberation is when sound returns in less than 0.1 second. It is in the middle between echo and in dead room, where dead room is a room without sound reflection. Okay, I will explain more on dead room later. So echo is a reflection of sound that returns after more than 0.1 second. So it is usually a result from reflection from hard surface, and minimum distance between listener and surface is at least 17.2 meter. So to explain more on reverberation versus echo, I will play this video. Let's hear what does it mean by a perfect place to sing. Now, that perfect place is because there is a good amount of reverberation. But what is it? Which part of the sound is the reverberation? I'm going to play this other video to show the difference of reverberation and echo.
Yo, 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 yo.
So in acoustic design, we don't want echo, but we also we don't want to add too many sound absorber until there's no sound reflection at all. If we did, we are going to get the dead room effect. So just now in this video, I hope you can see the difference between reverberations versus echo. Now, what is that room? This room here is filled with absorbent material. I'm going to play and we can hear what happened when there's too little sound reflection.
You can hear how the room deadens echoes by clapping constantly while closing the doors.
You can try to rewind to listen once again. Now, staying in that room for a long time, you will feel claustrophobic because you couldn't get the idea of that space when we didn't hear any sound reflection. There are two ways to reduce echo and control reverberation. We can absorb the sound or diffuse the sound. The combination of these two will produce better acoustic environment. So again, to make you understand more, reverberation time is the time it takes to decrease 60 decibel after the source has stopped producing the sound. I will explain more by using diagram. So when sound propagates away from its source, it becomes lower. So let's say the difference from here to here is 60 decibel. So the RT is over here, around 0.75. So to calculate reverberation time, we can use Sabin's formula, where RT is the reverberation time in seconds, V is for volume in cubic meter, and A is total absorption in square meter. So for A, you have to take the sum of total surface area times their absorption coefficient plus the sound absorption provided by furnishing or audience. By furniture, okay? By furniture or audience. So to get the total absorption, we need to multiply the absorption coefficient. So these are the absorption coefficient. Now there are different numbers of absorption coefficient for different frequency. For this exercise in this lecture, we will use 500 Hz. So here are the numbers. Now let's try to calculate. Let's do this together. So pause the video, take a pen and paper, or you can use your computer to calculate the reverberation time with me. Okay, hope you already have your pen and paper. So it says you are required to calculate. Okay, you are required to calculate the reverberation time of an office with dimensions 28 meter times 12 meter times 4.5 meter for the height, which has the following finishes and absorption coefficient. Now assume it is fully occupied with 20 people. Now before we go to the next slide, you might want to copy this. Okay, you can print screen or copy to your paper. From the given questions, extract the numbers. So ceiling size is 12 meter times 28 meter. So it's equal to 336 meter square. The absorption coefficient is 0.17. There's 4 face of walls. So this and this is the same. This one and this one is the same. So we will multiply by 2. Now 2 times 12 times 4.5. And then we have to add 2 walls times 28 times 4.5. So here are the numbers. And then this is the absorption coefficient, okay, 0.04. Next is the floor. The material is carpet. The absorption coefficient is 0.15. The surface area is 12 times 28. Last one, the absorption coefficient for each occupied seat, means people and the seat, is 0.8. We people also contribute as sound absorber. That is why you can hear echo more easily when you are in an empty room. Now, based on the extracted data, it is clearer and easier for you if you put it in a table like this. So based on Sabin's formula, RT equal to 0.16 V per A. So 0.16, and then the 12, this one is the volume. So take the 12 times 28 meter times 4.5 meter. And then this one here is based on the calculation here. You already get the area, and then you times multiply with the absorption coefficient. So make sure you get the same number with me. So combine all of this, and then you get the RT equal to 1.75 second. But what if it is empty? So just now is 1.75. So if it's empty, it's going to be, I already deleted this, so it's 1.98 second. So this one, remember the number, okay, 1.75 or 1.98, and the space is for office. Okay, so let's see whether it's suitable for office. Now, these are the reverberation time for different room type. Below 1 second is good for classroom and offices. You already get the answer here. So it should be below 1 second. So how about others? Okay, for 1 second is good for speaking, but not so good for music. Music will feel, you will hear the music as if it's a little bit dull. So RT equal to 1.5 second to 2.5 second is a good compromise if the room is to be used for both speaking and music. And then RT60 equal to 3.5 second is better for music. Okay, it's better for music and not very suitable for speech. And higher than that, 8 second, you see the difference? 8 second is, for example, for large medieval cathedrals, because they use organ music or with an accompanied voice. Here's another list of reverberation time for different places. The result that we got just now is 1.98. Now, based on this information, how to improve reverberation time? So office should be less than 1. So we can improve by referring back to this chart and choose materials with higher absorption coefficient. Maybe we can add acoustical ceiling. We can add acoustical ceiling or add drapery, okay? Or maybe add plywood panel at the wall. Or you can see here, you see the number. For acoustical coating ceiling is 0.75. Another one, for example, plaster is 0.04. So the higher the number, the better the absorption coefficient is. Let's move to the next subtopic, auditorium acoustic design. Auditorium is a place for listening, developed from the classical open-air theatre. So in these few slides, okay, when we're explaining about this, it includes any room intended for listening to music, theatre, okay, and theatre, classrooms, church, mosque, meeting halls, and others. So this is some basic things to know or consider when designing auditorium. We want to reduce or avoid noise and provide reasonable level of acoustic gain. For design consideration, in this lecture, we will learn about most of this. Okay? And when designing for acoustic, here are some things that we want to avoid. Speech intelligibility. So I want to explain this before we move forward. So speech intelligibility, or in a simpler term, speech quality, is a combination of power and clarity. So power is affected by distance from speaker, reinforcement by reflectors, reinforcement by loudspeakers, and sound shadows, and also others here, while clarity is affected by delayed reflections like echoes, reverberation, duplication of sound source by loudspeaker, ambient noise, and intrusive noise. So basically, in the next few slides, we want to have a balance of this. Depends on the function of the room. Okay. Now, room shape. How this affects sound. Room shape influence acoustic design. By designing using fan shape, for example, more audience can sit nearer to the speaker at stage. Okay, compared to if this one is box, okay, shoebox shape. The rectangular shoebox type here is excellent for music where reverberant sound is desired from far away. However, it is less suitable for a big speech hall. Now, referring to the fan and diamond shaped hall just now, by having splayed wall, okay, splayed wall, greater seating can be achieved. The wall also work as reflecting sound, okay, reflecting sound energy to the back of the hall. Next is room volume. Does room volume affect acoustic experience? Of course, yes. For lecture hall, we need to reduce room size, especially for unamplified room, means room without speaker. And because bigger room means bigger power output. Okay, power in terms of both speaker, both electric and our voice. So if we didn't use mic and speaker, means we have to speak louder. However, for music, okay, for music, larger room is desirable because we need the good sound effect. Okay, for music, larger room is preferable or desirable. Similar to point 1, it is best to place the audience as close as we can to the sound source, so we don't have to speak too loud, right? So next is on ceiling. I would like to recap what we have learned. There's reflection from flat surface and concave, and also convex. Concave and convex. So convex is similar to diffuse. So let's see the application for ceiling. Now for ceiling design, there's diffuser and reflector. In many large halls, ceiling reflector, or also called as cloud, are used to direct sound energy from the stage to the seating area. In some cases, the cloud also acts as absorber to avoid late reflection. So here are a few ceiling design and how reflection happen. Here, this one here with a concave ceiling is less suitable because it will cause focusing of sound at one point. So multiple reflectors here are able to spread. The reflected sound throughout the hall. Here are a few other effects by different reflector. This one here is flat reflector. So if the ceiling is tilted, wider reflection happens and more spread out effect happen with convex ceiling. For concave ceiling like dome, focusing will happen. Another effect is called creeping. This one, okay? That is, if you talk at the end of the ceiling here, even though with a medium volume, your friend at the other end can hear it clearly. Okay, this is because the sound is reflected along the ceiling. So since the second part of this lecture on sound and acoustic, we have seen the big convex reflector as diffuser. So these are the diffusers that work with similar principle as the big ceiling diffuser just now, but in smaller size. So there are a few types here. I believe you already seen some of these. Okay, for example, maybe this one. If not, now that you have learned about this, you can observe a hall or meeting room or mini study room, study room at your hostel, and see if you can spot these diffusers. So I'm going to play this video to help you to understand how diffuser work. Pay attention here. I'm going to play once again. So the sound is still reflected, but it's not reflected. It's not as if it's reflected from a flat surface. So in smaller hall, absorption is provided by audience. So remember in previous exercise, we learned that people absorb sound. However, in larger hall, more absorption is needed. So while early reflection from stage area is good, late reflection at the rear side, means at the back side of the hall, can cause echo. So the solution is to add more absorption at the sitting area and at the back wall. So I will share more on absorber. So there's acoustic foam. So this is aesthetically pleasant but less suitable for bigger space. So we have acoustic fabric panels that is made of wood frame. I think you saw a lot of this in lecture hall, wedding hall, or any other hall that you have been to. This one is easier to fit with any design because it is covered in fabric, means you can change it to any color. This one here, number 3, is absorbing underlayment. This is more common for floor. It is made from either foam, vinyl or rubber. Another absorber material here is acoustic partitions. It is usually made of 100% polyester. In some design, you can pin up on the partition. Next is acoustic cotton bed. So the advantage of this is it's natural. This one is natural cotton, means it's suitable for children and people who have sensitive skin. So remember, we are designing for human. Last one here is acoustic mineral wool, this absorber works as both sound absorption and soundproofing. And to add to that, it is also tolerant to high heat and can be fire resistant. So next one, we're going to learn about loudspeaker. So in a good hall or room, you can give speech without using a mic. But most of the time, we do need mic and speakers, okay, to increase the sound and minimize sound reverberation, and also to operate some musical instruments. There are three main types of loudspeaker system. The first one is centrally located system. This system has a single cluster of loudspeakers. Okay, pay attention here. This system has a single cluster of loudspeakers over a sound source, which means it is above the stage. So the second one is cluster of speakers, where two or more cluster of speakers are placed around the stage area, around here. So the last one is distributed system. So this one is suitable for halls with low ceilings and where sound has to be provided for overflow audience. So imagine if you're speaking here, okay, of course you need people at the back to hear. So it's very hard for us to speak louder, especially when the ceiling is very low. So we need speakers. This one you will see a lot in exam hall, because exam hall the ceiling are lower. So in certain cases we need this. So now imagine watching someone singing. Okay, well, of course watching and listening, and you can hear the singer's voice from the loudspeaker, but suddenly you hear an echo, and you realize that the echo is actually the direct sound from the singer. This happened because the singer's voice was transferred faster to the loudspeaker and reached the listener compared to the sound. Okay, stage here and the loudspeaker is here. So imagine you are over here. Okay, you can hear first the speaker and then only you can hear the direct sound from the singer. So to reduce this effect, we can use delayed system, where the sound from the loudspeaker is adjusted so that it arrives at the same time with direct sound. Another problem that can happen if we didn't use the delayed mechanism in loudspeaker system is you can hear the speaker first before you hear the direct sound from the singer, and the direct sound can be weaker than the loudspeaker sound. Now this is an ancient amphitheater. So we are now already at auditorium design. So note that over here, this part works as sound amplifier, this one here. Sound reflects at the wall and floor area here before reach the audience as loudspeaker. The sitting area is designed slopey to give good sight and low attenuation, means the audience is sitting nearer to the performer than when it is at the flat ground. So you imagine, let me draw something. So you imagine if this is, if singer is here and listener is here. Okay, imagine if we need to make it, we need to fit more people. So imagine this one but going up. Okay, so the number of people can be increased here. So maybe instead of standing here, we're actually standing here. So it's nearer. Okay. Here are a few auditorium design. The first one is outdoor with no slope, like Miller Outdoor here in Texas. Then the second one is outdoor with slope seating. This one here, Sarah Chandra Open Air Theatre in India. And this one here, Epidaurus in Greece. So this one is, the third one is with reflector behind the performer. So sound will be heard louder because it's reflected here before it reach the listener's ear. So one interesting example is Stone Nest Amphitheater in China, where it used natural stone as reflector behind the stage. For the one with stage shell, this is stage shell, the way it works is similar to this. So here are two examples. This one is Clock Tower at Vienna, and this one is Hatch Memorial Shell in Boston. So the Hatch Memorial Shell has one big concave structure around the stage area to reflect sound to the audience. For indoor auditorium, the ceiling acts as sound reflector too. You can see the difference. Designed for Petronas Philharmonic. Okay, this is Petronas Philharmonic Hall in KL, Walt Disney Concert Hall at Los Angeles, and Tokyo Opera City Hall, Japan. Notice that the Tokyo Opera City is using shoebox shape like this rectangular as the floor plan. Here are additional info for your reference later. Now I will explain more on music halls. Let's see the example of music halls design. So Petronas Philharmonic Hall is designed for classical orchestra or music. This grand hall provides acoustic environment for wide range of performance. The hall is built with its own concrete box with steel walls that reflect music and conceal air ducts. So let's see the section in the next slide. So notice the gap here, see? Because of the hall's busy and noisy surroundings, the audience chamber is mounted on resilient pads and structurally isolated from the rest of the complex. So remember, KLCC even has LRT below it, and it's surrounded by big buildings and a lot of busy roads. It also has special acoustically absorptive panels inside walls that can be opened or closed to adjust the resonance of the auditorium. So interesting design feature for this hall is the volume can also be adjusted by moving the reflective ceiling. So next we're going to see the design approach for office. So the design approach for office is different from auditorium, but it uses the same principles. Okay, a survey on occupant satisfaction with their workspace found out that intrusion of unwanted sound is the leading source of dissatisfaction. Workplace acoustic dissatisfaction could cause harder to do jobs, increased stress level, decreased motivation, and associated with risk factors for musculoskeletal disorder. Okay, what is that? That means a pain that affects the muscles, ligaments, tendons, and bones. The symptom of this is fatigue and sleep disturbance. So in general, we can say that improper office acoustic can affect our life quality. To solve this, the first thing to do is determine the need of employee. Do they need to communicate freely? with colleagues to do their job? Or do they need visual privacy and minimal speech privacy? Or need to be free from distractions, okay, to do more detailed work? But then normal speech privacy? Or the last one, maybe need confidential speech privacy where no conversation can be understood from adjacent space. Okay, for normal speech privacy, the suitable work situation is conversation in adjacent area can be understood. Means you can still hear your friend from other desks, but you don't want distraction, okay, because you need to complete the task. So this one require a proper design if have to work in open office. For the confidential speech privacy, you can't expect them to work in open plan. So must have a closed office with door and wall that extend to structural ceiling. So why it mentioned this? Okay, I will share in the next slide. Why do we need to extend the wall until the structural ceiling? Usually what happens is the wall for office rooms are just under here, under the ceiling below air con. So usually there's aircon ducting here, so sound can still be transmitted to adjacent area and speech can be understood clearly. So the wall must be built until the structural ceiling. Other than extending the wall to the ceiling, the structural ceiling, the other method is to use a cheaper material above the wall after the suspended ceiling. Okay, so for the following slides, we are going to focus on open office design for normal speech privacy. The rule to design for office is ABC: absorb, block, cover. So we will explain this more in the next slides. Now, office acoustic, the first one is absorb. So because it is an open office, there's limited wall. So the best is to install sound absorber at the ceiling. Then install absorber at wall and partition to reduce reflection. To minimize reflection, lighting with reflective surface shall be eliminated too. Okay, lighting with reflective surface is the one that you see at studio, the normal one, normal lighting. Other consideration is floor lighting, but if still needed, okay, you can use parabolic fixture that can diffuse sound more evenly. Last one for absorb is to install carpet on floor. Control impact noise such as heel clicks, drop objects, and others. After absorb is block. Now use 1.5 meter tall barrier. So the minimum sound transmission coefficient STC should be 25. Then arrange the workspace so that they didn't face each other, even with barriers between them. So this is to reduce diffraction. Okay, hopefully you still remember diffraction. Now, line of sight area need to be avoided. Add barrier to reduce it. This is line of sight. Means basically if you can see, you can hear, right? Last one, partitions should be flush into floor. So make sure there's no gap below here and no gap between the partitions and window sill. So we have to minimize any opening. Last step is to cover. By using sound mask, people can feel less annoyed with the surrounding sound. So we already explore and learned about this in our previous lecture. So that's the end of our lecture. Thank you so much, everyone. So please pay attention at reverberation and understand how to reduce noise.